China just did something the robotics industry spent 40 years insisting could not happen this decade. Not a lab demo, not a stage trick, an actual assembly line, pushing out full-size walking humanoid robots by the thousand, at prices that read like typing errors. And the strangest part of this whole story is that the breakthrough everyone is arguing about is not the robot at all. The claim sounds impossible. In one very specific way, it still is. But here's the part that makes this genuinely fascinating, and the part almost every headline about it has gotten wrong. What Chinese robotics companies did was not solve the hardest problem in robotics. They did something stranger. They found a way to skip it. They looked at the wall everybody else was trying to climb, and instead of climbing it, they rearranged the entire order of the problem so the wall came later. And once you understand what that actually means, you will see why engineers from Silicon Valley to Tokyo are watching these production numbers with a mix of admiration and something close to alarm. This video is going to break the whole thing down in plain language. No jargon, no spec sheet worship, no hype, just the real story of what China actually built, what it can and cannot do, why it matters, and what would have to go right for it to change the world the way people are claiming. There's actually a much bigger story behind all of this that I couldn't fit into this video, so I put it together in an ebook for anyone who wants to go deeper. You can find it in the description or scan the QR code on screen. Now let's get back to the video. To understand why this is such a big deal, you have to understand the rule that ran robotics for the last 60 years. It is not a rule anybody wrote down. It was just true, so consistently and for so long that the entire industry organized itself around it. The rule was this: do not try to make the robot understand the world. Change the world so the robot does not have to. That sounds cynical, but it is exactly what happened. The first industrial robot arm went to work in a factory back in 1961. It lifted hot metal castings and stacked them. It could not see. It did not know what a casting was. It repeated the same arc thousands of times a day with beautiful precision, and it worked flawlessly because engineers built a world around it where nothing ever surprised it. Bolt the arm to the floor, put the parts in exactly the same place every time. Fence it off so no human ever wanders inside. Control every variable, and the robot never has to think. That approach built the modern world. Every car you have ever ridden in was assembled largely by machines following that rule, and the results were staggering. Industrial arms today can position a tool to within a fraction of the width of a human hair, thousands of times an hour, for years without complaint. But there was always a cost hiding inside that success, and it has a name. Roboticists call it Moravec's paradox, and it is one of the most quietly humbling ideas in all of engineering. It says that the things humans find hard, machines find easy, and the things humans find effortless, machines find nearly impossible. Chess is hard for people. Computers crushed our best players decades ago. Advanced mathematics is hard for people. Machines do it instantly, but picking up a wrinkled shirt off a chair, walking across a cluttered room in the dark, opening an unfamiliar door with your hands full, a toddler does that without thinking. It took the robotics field half a century of work to get machines to do it badly. The reason is that your body is running an unbelievable amount of computation that you never notice. When you pick up a paper cup, you are estimating its weight before you touch it, adjusting your grip strength in real time based on friction you cannot see, correcting your balance for the shift in mass, and predicting what happens if it slips. All of it in a few hundred milliseconds, all of it below conscious awareness. Millions of years of evolution wrote that code. We just get to run it. So for 60 years, robotics split into two worlds. On one side, incredibly capable machines that only worked inside cages. On the other side, general-purpose humanoid robots that looked spectacular in videos and could not do a single useful job. And in between, an enormous graveyard of humanoid robot projects that ran out of money before they ran out of problems. Now hold that thought, because there is a second obstacle in this story, and it did not come from physics, it came from politics. Building a humanoid robot means building joints. Lots of them. A modern full-size humanoid has dozens of independently controlled joints, each one needing a motor, a gearbox to convert fast, weak rotation into slow, strong rotation, a sensor to know where it is, and a controller to drive it. That gearbox is the part that matters here. The precision reducers used in high-end robot joints were, for decades, dominated by a small number of Japanese manufacturers. If you wanted the good ones, you bought Japanese. Everybody did. It was one of the great quiet choke points of the industrial world. And then there is the other choke point, the one that has been in the news constantly, the most advanced AI processors. The chips used to train and run large models have been placed under export restrictions by the United States, limiting what can be sold into China. If your entire plan for a robot depends on the strongest available AI hardware, and you cannot reliably buy the strongest available AI hardware, your plan has a problem. So picture the position Chinese robotics companies were in a few years ago. The hardest unsolved problem in the field standing in front of them, a foreign choke point on the mechanical parts they needed, and an export wall on the computing parts they needed. By any normal reading, that is not a position you innovate your way out of. That is a position you retreat from. They did not retreat. They asked a different question instead. And this is where the story turns. Here is something that surprised me when I first started digging into the actual numbers, and it is the single most important thing in this entire video. Everybody assumes the bottleneck in humanoid robotics is intelligence, that the robots are not smart enough yet, that once the AI gets good enough, the robots will just start working. That is not what the data shows. Look at what these machines are actually being used for. Reporting on the Chinese humanoid sector through late 2025 found that more than 70% of one leading manufacturer's humanoid robot revenue came from research and education customers, universities, labs, training programs. Demonstration units, industrial applications, meaning robots actually doing work in actual factories, accounted for around 9%. 9%. Sit with that number for a second, because it reframes the entire conversation. The overwhelming majority of humanoid robots being sold were not going to work. They were going to be studied. They were being bought by people whose job is to figure out what to do with them. The machines were shipping. The jobs were not. And that gap, the gap between a robot that exists and a robot that earns, is the real bottleneck. Not intelligence in the abstract, experience. These machines have almost no experience of the physical world, because almost none of them have ever been given a real job to do. Think about why that matters. The AI models that write and reason were trained on essentially the entire written output of humanity. Trillions of words sitting on the internet, free to collect. Now ask yourself where the equivalent dataset is for physically manipulating objects. Where is the archive of 100 million examples of hands opening jars, folding fabric, seating a bolt, catching something that slipped? It does not exist. It was never recorded. Every single hour of that data has to be generated by a physical machine physically doing the thing in real time at real-world speed. And there is no shortcut. You cannot download the feeling of a screw threading correctly. That is the wall. And it is a nastier wall than it looks, because it is circular. To get the data, you need robots working in the real world. To get robots working in the real world, you need the data. Every serious humanoid program on Earth has been staring at that circle. So here is the insight that changes everything, and it is the reason we are having this conversation at all. If the bottleneck is not brains but experience, and experience can only be generated by machines that physically exist, then the constraint is not how smart your robot is. The constraint is how many robots you can put into the world, and how cheaply. Do not solve intelligence first. Solve volume first. Build the body so cheap and so reliable that thousands of them can be out in the world grinding through real hours, and let the experience accumulate. Turn a research problem into a manufacturing problem. And here is why that reframing is so uncomfortable for the rest of the industry. Manufacturing at enormous scale, driving costs down relentlessly, iterating hardware fast, and standing on top of a fully domestic supply chain is the single thing China's industrial system is best in the world at doing. They did not outthink the problem. They rotated it until it pointed at their strongest muscle, and the pieces were already sitting there, which is the part most people miss. The electric vehicle boom had already built out exactly the components a humanoid robot needs. High-performance electric motors made by the million, battery cells and battery management systems mature and cheap, power electronics, motor control expertise, sensors, precision machining at volume. A humanoid robot is, from a parts perspective, a strange-looking electric vehicle with more joints and worse aerodynamics. The supply chain was already standing. It just needed pointing in a new direction. Meanwhile, the choke points got attacked directly. Domestic precision reducers, domestic motors, domestic encoders, and on the computing side, some companies stopped waiting for chips they could not reliably buy and started designing their own. One Chinese electric vehicle maker moving into humanoids built its robot around 3 of its own in-house AI processors, reportedly delivering around 3,000 trillion operations per second when combined. Another company's flagship humanoid platform advertises compute in the range of 2,000 tops on board. Those are not consolation prize numbers, those are numbers built by companies that decided the export wall was a design constraint rather than a stop sign. Now let us talk about the number that actually made the rest of the world sit up, because it is not a spec. It is a production figure. According to figures disclosed by an official from China's Ministry of Industry and Information Technology, humanoid robot output for 2026 is projected to exceed 100,000 units. The comparable figure for 2025 was roughly 20,000. That is a 5-fold jump in a single year. Let me put that in context. For most of the history of this field, the total global population of full-size humanoid robots that could reliably walk was measured in the dozens. Hundreds if you were generous about what counted. The entire field was small enough that specialists knew each individual machine by name. Now we are talking about 6 figures in 1 year from one country, and underneath that headline sit the individual companies. Reporting on the sector describes 2 firms forming something close to a duopoly at roughly 15,000 and 11,000 units respectively, with one of them targeting a full-year shipment figure of 20,000 and planning to scale annual capacity toward 30,000. Another established manufacturer reached its 1,000th unit of a single industrial humanoid model coming off one factory line. That is not a prototype milestone. That is a manufacturing milestone. Unit number 1,000 means the tooling works, the process is repeatable, the suppliers are keeping up, and somebody has solved the deeply unglamorous problems that never make it into a launch video. Then there is the price, which is where it stops being an industry story and starts being a story about your future. In mid-2026, one major Chinese manufacturer launched a full-size consumer-oriented humanoid series explicitly designed for mass production, with pricing starting from around 119,800 yuan and reported cumulative orders above 13,300 units as of the launch. Translate that starting price roughly into dollars, and you land somewhere in the range of a mid-tier family car. Not a research grant, not a defense contract, a car. Hold that thought about price, because it comes back at the end of this video in a way you might not expect, and it is the part almost nobody talks about. So on paper, the roadmap looks extraordinary. Domestic supply chain, collapsing prices, 5 times the production in 12 months, and a strategy that turns the field's hardest problem into a manufacturing race. If you only read the headlines, you would conclude the humanoid era has arrived and everyone else is already too late. But this is the part of the story where physics shows up and starts asking difficult questions. Because there is a wall in front of this plan too, and it is made of 3 separate problems stacked on top of each other. The first is energy, and it is brutally simple. A humanoid robot is the least efficient shape you could possibly choose for a machine. Wheels are efficient. Rolling is efficient. A 2-legged body is a controlled fall that has to be caught thousands of times an hour by motors that burn power just to keep from tipping over. And unlike an industrial arm, which plugs into a wall and never moves, a humanoid has to carry its own energy on its back. Look at the numbers on one leading full-size platform. Around 182 centimeters tall, roughly 70 kilograms, with a battery in the neighborhood of 970 watt-hours, delivering something like 3 hours of runtime. 3 hours sounds acceptable until you compare it to what it is supposedly replacing. A human worker does an 8-hour shift. A conveyor belt runs for years. So either your robot works part-time, or you build swappable batteries and charging infrastructure and enough spare robots to cover rotation, and suddenly the economics you are selling look very different. Battery energy density improves slowly, painfully slowly. It is one of the few areas of technology where progress has been measured in single-digit percentages per year for decades. There is no version of this where somebody announces a battery breakthrough next quarter and the problem disappears. The second problem is the hands, and this is the one that keeps engineers up at night. Everything impressive you have seen a humanoid robot do in a video is almost certainly locomotion. Walking, running, backflips, spinning kicks. Those are genuinely hard and genuinely solved to an impressive degree, largely because they can be trained in simulation. You can run a virtual robot through millions of simulated falls overnight, learn what keeps it upright, and transfer that to hardware. Gravity is easy to simulate. Balance is easy to simulate. Falling over costs nothing in a simulation. Manipulation is different. Contact is different. The moment a robot touches something, the simulation starts lying. Friction between two real surfaces, the way a soft object deforms under pressure, the microscopic slip when a grip is not quite right, the flex in a joint under load, the subtle stickiness of a rubber glove on a glass jar. All of that is extraordinarily difficult to model accurately, and the errors compound fast. That is why the videos show robots doing backflips instead of loading a dishwasher. A backflip is a controlled interaction with one known surface. A dishwasher is 1,000 unpredictable contacts with wet, slippery, differently shaped objects, any one of which can fail. And a human hand has something like 27 degrees of freedom with tens of thousands of sensory receptors in the skin. Advanced robot hands are getting genuinely better, with tactile sensing and 5-finger designs shipping now, but the gap between an impressive robot hand and an ordinary human hand is still measured in orders of magnitude, not percentages. The third problem is the one that ties the other two together, and it is the least discussed: reliability. A demonstration robot needs to work once in a controlled space, with engineers standing by. A commercial robot needs to work every day for years in a dusty factory at temperatures nobody planned for, without a specialist in the room. Every one of those dozens of joints is a mechanical component under cyclic load. Gears wear, bearings degrade, cable harnesses that flex 1,000,000 times eventually fail. Heat builds up inside joint housings that have almost no room for cooling, and heat is what quietly kills motors and electronics. And there is a second-order version of this problem that almost nobody outside the industry thinks about. When an industrial arm breaks down, a specialist opens a panel, swaps a known part, and the line restarts. When a humanoid with dozens of joints and a walking gait develops a fault, diagnosing it is genuinely difficult because the symptom and the cause can sit in completely different parts of the machine. A slightly worn gear in one hip can show up as an unstable arm because the balance controller is compensating for something upstream. Building the robot is one engineering discipline. Keeping 10,000 of them running in the field for a decade is a second discipline, and hardly anybody on Earth has done it yet at scale. And there is a hint that this gap is already visible in the market data. One report on the sector noted that a major manufacturer ranked third in production but slipped to fourth in shipments, and pointed out what that pattern usually indicates. Robots being built faster than they are being delivered. Inventory accumulating. That is the numerical fingerprint of the distance between manufacturing something and successfully putting it to work. So that is the honest shape of where things stand. The production is real, the prices are real, the engineering challenges are also real, and they are not the kind that get solved by an announcement. Which brings us to the question the title of this video is really asking. Is any of this actually the most advanced humanoid robot in the world? And here is where I have to be straight with you, because there is something about that phrase that a lot of coverage gets wrong. There is no measurement for most advanced. None. It does not exist. For chips, at least there are benchmarks. For phones, there are tests. For humanoid robots, there is no agreed standard, no shared test, no independent body running the same task set across every machine. So the specs get used as stand-ins, and the specs are far weaker evidence than they look. Take degrees of freedom, the count of independently controlled joints. One flagship platform advertises 31. It sounds like a capability score. It is not. More joints means more ways to move, and also more mass, more cost, more failure points, and vastly more control complexity. A robot with more joints is not automatically more capable, in the same way that a car with more cylinders is not automatically faster. Take TOPS, the raw compute figure. It measures how many operations the onboard hardware can theoretically perform. It says nothing whatsoever about whether the software running on it knows how to fold a towel. Compute is the size of the engine. It is not the skill of the driver. Take joint torque, or height, or payload. All useful engineering figures. None of them tell you whether the machine can handle a task it was not explicitly prepared for, which is the only thing that actually matters for a general-purpose robot. And this is exactly why so many of these launch demonstrations are argued about online. One of the most talked about Chinese humanoid unveilings in recent years produced a robot so fluid on stage that viewers openly accused the company of putting a person in a costume, and the company had to cut open the machine's outer covering in public to prove there was no human inside. That tells you something real about how far the hardware has come. It tells you nothing about whether the same machine can work an unsupervised shift. So the accurate version of this story is not that China built the single most advanced humanoid robot on Earth by some objective measure that does not exist. The accurate version is more interesting than that, and here it is. China is currently ahead on the axis that its competitors were not optimizing for: volume, cost, supply chain depth, iteration speed, number of physical machines in the physical world. And if the theory at the center of this video is right, if experience really is the bottleneck rather than raw intelligence, then that is the axis that eventually decides the whole race. The rest of the world noticed. American programs are pushing hard toward their own mass production, with reporting on one high-profile effort describing an entire existing factory being converted into a dedicated humanoid production line and supply chain sources pointing to weekly output targets in the thousands. Japanese and Korean manufacturers, with generations of robotics heritage, are moving too. At recent major technology exhibitions, Chinese firms have made up over half of the humanoid robot exhibitors, which is a statement of intent all by itself. This is not a finished race. It is a race that just changed its measurement. Now let us zoom out and ask the bigger question. Even if all of it works, what does it actually change? There is a temptation to compare this to the computing revolution, where things got cheaper and better at the same time, generation after generation, until computers ended up in every pocket on Earth. That combination of falling cost and rising capability is close to magical, and it is what people are imagining when they picture a robot in every home. But cheap humanoid robots do not automatically follow that curve, and it is important to be honest about why. Falling price is not the same as rising capability. You can cut the cost of a body to a fraction of what it was, and still have a machine that cannot reliably do a useful task, because the bottleneck was never the price of the body. It was the competence. What cheap bodies actually buy you is something subtler and, in the long run, possibly more powerful. They buy attempts. When a research humanoid costs as much as a house, only a handful of institutions on Earth can experiment with one, and each of them is careful with it because it is irreplaceable. When the same class of machine costs as much as a car, thousands of teams can try things: universities, startups, factories running small pilots, individual engineers in a garage, and most of those attempts will fail. That is the point. Progress in a field like this is not driven by one genius insight. It is driven by the number of shots on goal, and cheap hardware multiplies the number of shots enormously. That is the actual mechanism by which this strategy could win. Not because a cheap robot is a good robot, but because 10,000 cheap robots produce more real-world lessons in a year than 100 expensive ones produce in a decade. And there is a compounding effect buried in there too. Every hour a real robot spends doing a real task in a real building generates data that nobody had before, and that data can be used to train the next version of the software, which gets pushed back out to every machine in the fleet. That is how the loop closes. One robot learning something awkward about a slippery handle in a warehouse in one city can, in principle, improve every other unit of the same model everywhere. A fleet of 10,000 machines is not 10,000 separate learners. It is one learner with 10,000 bodies, and that is a fundamentally different kind of thing from a lab prototype, no matter how impressive the prototype looks on stage. Which is why the price point I mentioned earlier matters more than any specification on any launch slide. Price is not a marketing detail here. Price is the throttle on the rate of learning for the entire field. So what should you actually watch over the next couple of years if you want to know whether this is real? Watch the industrial revenue share. Remember that 9%. If the fraction of humanoid revenue coming from robots doing genuine paid work in genuine workplaces starts climbing and keeps climbing, that is the strongest possible signal that the flywheel has caught. If it stays flat while production keeps rising, then what is being manufactured is inventory, not adoption. Watch reliability numbers rather than capability demos, mean time between failures, maintenance intervals, hours of operation between service. These figures are boring, unglamorous, and never featured in a launch video, which is precisely why they are the honest ones. A company confident enough to publish uptime data is a company whose robots are actually working. Watch the hands. Not the walking, not the flips, not the dancing. Watch for demonstrations of manipulation on objects the robot has not seen before, filmed in one continuous take, at real speed, without cuts. That combination is the hardest thing to fake and the single best proxy for genuine progress. Watch how much of the work is autonomous versus remotely operated by a human. Teleoperation is a completely legitimate way to collect training data, and much of the industry uses it deliberately. But a teleoperated robot is a very expensive puppet, not an autonomous worker, and the ratio between the two is the truest measure of where the field really is. And watch the price floor. If full-size humanoids keep getting meaningfully cheaper year over year without capability going backwards, that is the manufacturing flywheel doing its work. If prices stall, the volume strategy stalls with them. Here is where I have landed after going through all of it. The impossible thing in this story is not a robot that walks. Robots have walked for years. The impossible thing is that a category of machine which spent half a century as an expensive scientific curiosity became a mass-manufactured product at consumer-adjacent prices on a timeline almost nobody in the field predicted. That part genuinely happened, and the production numbers are not marketing. What has not happened yet is the second half. Nobody has demonstrated a humanoid robot that reliably does economically valuable general-purpose work without a human in the loop anywhere on Earth. Not in China, not in the United States, not in Japan. The bodies arrived before the minds did, and the gap between them is still wide open. But there is something worth sitting with in how this unfolded. For 60 years, the field assumed the humanoid robot problem would be cracked by whoever got smartest first. What happened instead is that a group of companies decided the path ran through the factory floor rather than the research lab and started building the machines by the thousand while the argument was still going on. Maybe the fairest way to put it is this. They did not find a way through the wall everyone else was pushing against. They found a door somewhere else in the same wall, walked through it, and are now standing on the other side, finding out what is actually there. Whether that ground leads where they think it does is something the next few years are going to answer in public, in factories, with numbers that are very hard to fake. That is the full story of what China actually built, what it can and cannot do, and why the robotics world is watching so closely. If you made it this far, drop a like on the video. It genuinely helps this channel reach more people who want the real version of these stories instead of the hype version. Subscribe and hit the bell so you catch the next deep dive when it drops. And I want to know what you think. Is cheap mass production really the path to capable robots, or is the world about to be filled with 100,000 machines that still cannot fold a shirt? Let me know in the comments.